because the main part of my talk will be about one chunk of science, and it is a multi-experimental and multi-computational approach to tackle this question. Okay, so my group is interested in finding out what the real structure is of a metal organic framework, all the disorder and so forth, and to also look at the actual dynamics. So in photocatalysis, and also photocatalysis to find out what are really the photodynamics, where are the photoexcited charges, how long do they live, and so forth, to come up with design rules, sorry. And also we like to look at how these materials actually dynamically evolve during growth. And indeed, I'm a mostly experimental scientist. And even if we want to answer questions that are difficult to answer with current techniques, we even actually develop new techniques, new spectroscopic techniques. But today I'm going to mostly talk about a topic that is more recent in my interest, and that is about the structural dynamics that MOFs have by themselves. So would it be possible to start this video? Yes, thank you. So this is not a creative depiction of a MOF, what you're looking at. It's actually ab initio molecular dynamics calculation, just showing the native behavior of the MOF, which is extremely dynamic. There is movement going on all the time. And a lot of this movement is due to the linkers, in fact. So you can, if you think about rotational dynamics of the linker, you can think of a linker in terms of where it's connected to the framework, a static, then you have a rotating part, and then you will have some covalent bonds or coordination bonds that keep this rotating part in place. So you can think of this A-type, or you can do full rotations, or the rotation could be limited to librations, or you can have a functional group around a side group that rotates, or even what is very beautiful chemistry, have interlocked parts here. And if you're interested in knowing the extent of research on this type of dynamics in MOFs, we recently published a review on that. To go a bit on the state of the art, yes, the rotaxanes here yes. The rotaxanes here, this is very beautiful chemistry, which was achieved, for example, by the loop group, and which you can actually use as a shuttle motor. And also this C system here that you see is also something that actually has been exploited as a molecular motor in a MOF, where you can, with light, get something to rotate. And if you like to know more about motors in MOFs, you can check out this recent review by Krause and Veringa. Okay. So the question, of course, is that why do you care about these linker dynamics? Okay, they are happening all the time, but do I really need to understand that to understand my material? And I would say, yes, you definitely do. So what you see here, for example, this is mil 47, where, well, this was actually my master thesis work, long time ago, not this paper. Paper is a lot older, where we showed that it preferentially absorbs peroxylene out of a xylene mixture. And a far more recent paper by Guy and Scholl, they've shown that if you start to model this and you do not include these linker dynamics, you just treat a static framework, the results, the selectivities that you predict are very far off the actual measured selectivities. Okay. So, but there are also more, so absorptive separations are by far the most close to application properties of MOFs, but you can also think about the impact of rotational dynamics in more fancy properties, like the optical properties. So here is work where we've shown for amino mil 53 that in the static closed framework, we can actually generate frequency double light. Well, this is not possible. Well, this disappears actually when you open the framework and the linkers start to rotate. Also, in the same year, the Dinka group showed that you can, via this molecule the linker molecule here, that doesn't show fluorescence due to rotational dynamics. By embedding it in the framework, the rotational dynamics are sort of damped and you get more fluorescence out. And of course, it will have an impact on mechanical properties. Oh. And if we then look at the papers that have specifically looked at studying rotational dynamics for the sake of the rotational dynamics of MOFs, what you see is that this literature is focusing a lot on creating ultra-fast rotors. For example, if you build in this molecule that you see here, in a framework where it's not sterically hindered by anything else, because this is not an aromat, you don't have the electronic stabilization, so it can rotate really very fast. So in terms of studying the rotational dynamics of MOFs and gearing them towards a certain behavior, this would be the state of the art. Okay. But I have another goal, actually. So I'm interested much more what happens when things get crowded, when there is actually linkers close to each other that could influence each other because they are sterically close. You can think of this, if you see a crowd, like on this picture, then you get certain flows to the crowds, through the crowds that are determined by the persons that are standing next to you, right? That's a very macroscopic view. But in nature, you would see the same behavior, for example, if you look at a lipid bilayer. You get areas where sort of you get sort of a cooperative motion of these phospholipids together because they are hindered by each other. So I would argue interesting things happen when you get dynamics of molecules that are very close together. And the MOFs, you have a very interesting situation because you have a pore space and a topology where you can sort of tune how much steric hindrance you could have between the linkers. So you have a handle. And you can actually establish or create things when you think of cooperative motions. This is, for example, material from polymer chemistry. You see sort of these yellow polymer threads that have that can undergo a trans-cis isomerization under the influence of light. So when light shines in, it goes to cis and it pulls together. It's sort of like it can pull together and apart again like a artificial muscle. Okay, this is a little bit hard to imagine a MOF doing that since we are sort of confined to a crystalline structure. It becomes a different story if you think about the woven networks that Omer Yagi was talking about yesterday. Then you could imagine that if you could make this work cooperatively like this, maybe you can make an artificial muscle. But bringing this a little bit closer home to what you can do with cooperative motions in MOFs would be, for example, a recent paper by Jack Evans and collaborators, where he was studying theoretically how if you would have rotating units, motors in the pores, would this influence the diffusion of the molecules? So could you make it directional, slower, faster, and so forth? And what they found out is that having the motion of the motors correlated to each other, like a certain in phase or exactly out of phase, and how they exactly work together, is extremely important. So I would argue that seeking out such cooperative motions in MOFs could be very interesting. So I wanted to find that type of behavior to see if it would already be naturally occurring in MOFs if the linkers are simply close enough together. So you see here 3 examples of quintessential MOFs. We have MOF 5 here, we have UEO 66 and MIL 53. For all these 3 MOFs, sort of the rotation for a activated structure of the linkers has been investigated, and in all 3 cases they behave like free rotors. There's no steric hindrance. But you can imagine that if you look at MIL 53, that the distance between these neighboring terephthalates along the pore direction is much closer than in UEO 66 or MOF 5. In fact, if you look at the distance, yes, then what you see is if you place the terephthalic acids such that they are as close as possible, that the distance between the hydrogen atoms, the closest distance, is about 2.3 angstrom. That means that they're van der Waals radii or barely touching. So they're extreme. It's just off touching. So whatever you would actually add to this linker would create steric hindrance between the terephthalic acids along the pore direction, so the pore wall in MIL 53. Okay, so we picked on 3 examples to show sort of the diversity of rotational behavior you could get. So we focused also on simply the unfunctionalized one, where we know it's unhindered rotation. And at the extreme opposite end, we take the amino-functionalized one, because on the one hand, you have these narrow pores there, so there should be very much steric hindrance. There's also this hydrogen bond between amino group and the oxygen of the framework that really makes it also energetically less favorable for the linker to rotate. In the middle, we thought, okay, if we take a nitro functionalization, that should be very interesting because on the one hand, it's a bulky group, relatively bulky, but the pores are open. So it might be sort of a medium steric hindrance situation. And if we looked at the energy that it takes from its lowest energy conformation towards a 90 degrees rotation, we saw that that energy barrier of 17.1 kilojoules per mole is actually quite low. So it's it should be quite dynamic linker, though it is sterically hindered. Okay. 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 So first of all, the PhD student did was to look at how exploring this rotational space with DFT. So you see here the amino group in a narrow pore, and you see here the graph that I'm afraid is not so clear. But if you look here in the middle, thank you. You see that you have this orange graph where the energy is increasing extremely fast if you try to rotate the linker, and is not so strange, because if you then just take a look at the structure, what is happening, you simply see that this linker that we try to rotate is immediately bumping into the upstairs neighbor. So you can imagine, like we thought, no meaningful linker rotation will be happening in this material. If we do the same thing for the nitro linker, and then you should look at this green graph, we see an energy landscape where we can actually rotate the linker, and an energy barrier that is modest of 40 kilojoules a mole, which seems to indicate that it can freely rotate. But this is a little bit, this is rather misleading, because it's done in a single unit cell. So all these neighboring linkers that are sitting close to each other, they're rotating synchronous. So we doubled the unit cell to see what happened if we would rotate one of these linkers independently. And then you see that you can come in situations where the energy rises extremely fast. And that's also not so surprising. You can come then in situations where indeed this linker is bumping into the next neighbor. So our intuitive prediction that we would have steric hindrance here is the case. So indeed, we have crowded rotations along the pore direction. Thank you. Okay. Experimentally, the very easiest thing you can do to study linker dynamics is to use, if you have dipole or linker molecules, is to use broadband dielectric spectroscopy, where you just make a capacitance of your MOF powder. You just make a palette of your MOF, basically put it between electrodes, and then you get you can measure a charge, or sorry, a voltage, an alternating voltage is applied between the electrodes. And if there are dipolar motions that are at the same, that are naturally happening at the same frequency as this alternating electrical field, we get sort of a dielectric loss. We see it in the complex part here. So that is what we are going to look at. And it shows a very clear picture. So what you see is that there is hardly any dielectric loss happening for the unfunctionalized linker, but that's logical because there's no dipole here, so it can move as much as we won't see it. We're sort of blind to it. The amino one is one which we should be able to see if it would be moving, but also here we get no signal, so that would indicate there's simply no dynamics. And for the nitro one with the dipole, we see clear loss peaks where the frequency, the frequency of maximum loss is increasing here from 2.5 kilohertz to 1 megahertz at room temperature. Okay. Yeah, so what is the take-home message from this measurement here is that you have dynamics over a very wide frequency range. And what is interesting also is that if you plot these peaks, the shape to a what they call call plot, you get, I'm not going to go into physics of it, but you get a certain parameter alpha, which is here, if it gets close to 0, that means that all these linkers are basically rotating in the same way. And if it's getting higher, then you get sort of a big diversity in how the linkers are rotating. They might experience different environments. And what you see here is that as the temperature lowers, that more complex situation is actually emerging. Okay. But you can get this, so BDS is sort of very easy to do and gives you some clear information, but it doesn't show you like, is this a small rotation? Is it a 180-degree flip? If you want to have detailed information, you need to go to solid state deuterium NMR. So we did that. That also meant making deuterated versions of these linkers. And you can see basically this is for the unfunctionalized MIL53. It's doing exactly what we expect as the temperature rises. We get a higher frequency of 180 degrees pi flips, and the amino one is static. But it gets much more interesting if we go to the nitro one, actually. Because if you look close at this shape, I'm wondering a little bit, we were completely puzzled by this shape, actually, because if you look at it, what you basically have is in the static motion limit, so those two peaks, and then superimposed you have the very fast motion limit, as if you, and then you see a situation emerging where you go from static to very fast, where you simply have a superposition of both in between here. And that's very strange. I was wondering a little bit. So we went all through literature to find if we could find any MOF that sort of showed this kind of NMR patterns, but we couldn't find them. So if you are aware of them, then maybe put it in the Q&A, then I can see it. But it's actually, it is something you can find in polymers, for example, where you have rotating benzene rings and where you have much more crowded situations and so forth. What is actually happening in reality here is that we have a very broad frequency range of rotations. The dielectric spectra also told us that. The intermediate region definitely is also present, but it's just that it's with the precise settings of this instrument, it's the physics of this system, it's less sensitive to that. So because we have both a fraction of static and very fast moving, they dominate, and it looks like that. Okay. And then we could model that based on what we knew from DFT and ab initio molecular dynamics we did. We came with a model that we should have a foresight with 60 degrees and 120 degrees jumps, and that was also what fitted these data the best. So you see that quite a complex situation is emerging here, that it's, and still we haven't come to my central question of what I really set out to know is, what about cooperativity? I've shown you that we have crowded complex rotations, but not necessarily that linkers are moving together. to do that, we did, again, ab initio molecular dynamics, but this time in a double unit cell. Because otherwise, if we have a single unit cell, we make each of these linkers rotate synchronous and sort of, and we want to investigate if they like spontaneously have some synchronity in their motion. So we need to allow them to have their own motion, the two linkers. Okay. And this would be a good time to just show the slide again. Thank you. So this is one of the many MD traces that we calculated, but it's a very nice example to look at, because I'll guide you through the figure here. In the light pink, there is the one pink, the angle of the light pink of this linker. And then in the other pink, you have the rotational angle of the left linker. And what we've also plotted here is basically the distance between the nitrogen atoms of the nitro groups, because you can imagine when they're close, like here in the orange rectangle, you see that they're like around 4 angstrom, which is really close. You expect steric hindrance. And if you are much higher values, they're far from each other and shouldn't influence each other. And what we indeed see emerge is that if you look at the pink, the two pink traces within the orange box, that you sort of see them all the time moving out of phase. As one is going up an angle, the other is going down an angle. Sort of reacting to each other. If you look outside of that window, you see a lot of motion in the dark pink linker, but hardly any in the light pink linker. So they're hardly influencing each other. And that's also not surprising, because the distance between the nitro groups is pretty far. And if you then want to look at, it's interesting to then look at, if you want to know what is exactly happening, to look at the actual structures. Okay. So here you see these dotted blue lines. They are 4 conformations that you here see. You start on the top left and you end at the bottom right. And what you see basically is that as one linker is, and now it would be convenient to show me again as well. Thank you. What you basically see is that as the nitro group is sorry. Is in the first image, it's like this, and then you see it moving like this and like this until it sort of emerges. So you get a lot of motions, fluctuations like this, and finally movement like that, where they're moving together. And this isn't cherry picking, because you might think because I just show you one, but if we look through our data, this is a pattern that emerges. Of course, sometimes you also see this, they come together and they go away from each other again, but that is much more rare. So what we want to state here is that we see a gear-like cooperative motion emerging. Okay. Okay. Oh. To come to the conclusion here is that indeed, if you come to a sort of sweet spot in distance and steric hindrance with linkers, you can start to see the emergence of collective motions. Of course, the next step would then be to start to control that with an external force and create cooperative motion over a long distance. And potentially, I think we actually ideally have even more steric hindrance than in this MOF. I think I'm not doing well on time. I suspect my time is practically up. I had prepared another small topic of a technique we developed to probe crystallization of MOFs, but I suppose that if you're interested, you can go read the paper. I'm going to the next slide. Yes. So there is the reference given, where we could basically follow the symmetry of the first appearing nuclei of Civ8. That's actually what we did there, which was pretty cool, but it's for another time. I'd like to go to further slides, to the thank you slide. Yes. Oh, too fast. Yes. So I wanted to thank the people that already on the first slide actually was everybody that contributed to this gear-like motion paper. The QR code, by the way, that you saw during the paper is where you can go to the preprint that is available already. I want to thank the funders, the collaborators, the team that I enjoy working with, and you for your attention.